Bismillahirrahmanirrahim. Hello, my friends. This is Dr. Mohamed Nezami again with another session on my flat panel antenna array feed networks or microstrip array feed networks or planar array feed networks. This is the fourth session part and probably the last one on the design and modeling of these microwave circuits. I'm a design consultant. I design out of circuitry. I operate out of Jerash, Jordan. That's what you see in the background here. My native city, Jerash, ancient Roman city. I operate out of here, so it's very inexpensive compared to the Western Hemisphere. Please do contact me on this number here or on this email if you have any design, outsourcing design opportunities for your organization. It's impressively low cost. I work with you from schematic, from concept to specifications to system modeling to circuits designs, active and passives from DC to 35 gigahertz. And then I work with you all the way to turning in Gerber fab files and bill of materials. I also do follow up with designs even after prototyping. So I welcome you to contact me. Very reasonable, cheap prices for design and very determined from the beginning estimate number of hours. So again, like I said, this is the fourth session into the antenna array feed networks. We have covered, this is my microwave channel here. Let me reduce this a little bit. This is my YouTube channel. And right now we have covered, this is part 1, part 2, part 3 of the feed antenna network design and modeling. And today, probably the last session in this series is we're going to cover the sequential rotation of feed networks for circularly polarized array antennas, and even for linear antennas where we use this technique to create circular polarization. So in the please go ahead and view these videos before, and please subscribe to the channel and share it if you could, so we can broaden the audience of the system of the channel, so that other benefits as well. So part 1 and part 2 and part 3 are relevant to what we're going to cover today, which is the modeling of sequential rotation feed networks. And it's pretty simple. It's just about, we're going to cover it right now. So let's go ahead and do that. Let's put this into presentations. So like I said before, as you may know, flat antennas are really becoming widespread and becoming the choice and the only choice sometimes. Primarily due to the easiness of fabbing and lightweights, and they're more easier to do 3D printing and use modern manufacturing techniques. And you've seen probably the Starlink is the most famous recent antenna panel for the ground terminals that people have looked at. And then we've got the 5 and 6G antennas that are coming out with the integrated phase array networks in there, or car radars sometimes. So just to define the concept, what is the circular polarization? It's basically an antenna which is fed in quadrature or fed orthogonally with 2 feeds of the same signal, and sometimes the different signals, like in the case of the Starlink, each the vertical and horizontal, even home SATCOM channels, you have totally independent channels on the vertical and horizontal. So there are 2 separate information paths, but nevertheless, they still are fed feed the antenna the same way. So for reference plane X and Y, like I presented in this sketch here, which is orthogonal to the direction of radiation in the Z direction, that's inward or outside of this page, there are four polarization given by choices by the following normalization field vector, and that's the vector you multiply the transmitted or received signals, so you can actually do orthogonalize it or demux it. And that's basically, we have a 2x1 matrix for the circularly polarized signals, and they could be either left-handed or right-handed, and that just basically is a matter of whether it's rotating clockwise or counterclockwise, and we represent that by just a negative sign on the J. So if you're doing X plus JX, we're basically going counterclockwise, and that's a left-hand rotation, and vice versa for the other direction. Linear polarization, whether it be horizontal or vertical, we null out one of the X and Y independently, so that if the X is 0, that means it's vertical. If the Y is 0 in this matrix, that means horizontal. Okay, so basically antenna arrays, like antenna arrays networks that we have covered in the past 3 sessions, and you could get back to them. Most of the arrays that are present nowadays in research and in manufacturing are really based on the use of a T-junction splitter. And that's basically starting out right here where we feed the signal, we split off with a T-junction in here for this subarray, and then we split again with T-junctions, and in here you can see that the impedances are different, which means the power level are different between this subarray and this subarray. And we've covered that in the past sessions where we made design equations for the T-junction splitting and how to use tapering, tapered array, and figure out all the T junctions for all the antenna elements. Okay. So here's just an example of these conventional arrays. Basically, we have an array here. In the blue here is the antenna feed array network. Okay, and then we have a slot in the ground, in a ground plane, right, and right above it, and that which leaks in the signal to the square batches on top, and that's what you see in the fab file in here, where the middle slotted layer slots are not shown in this case. They were not reported in this reference. So now another one we covered is basically the use of Wilkinson dividers. We know that these T-junctions in here are basically not fully matched on all sides. And so sometimes some people utilize Wilkinson dividers, and in this case you can see that the horizontal and vertical polarization feeding on the top and the bottom is basically this is the feed network based on Wilkinson dividers. And then the last 3 videos, one of them was fully dedicated for this type of antenna feed network. So let's get to today's topic. Today's topic is the sequential rotation-based feed network. And that's basically where we come into an array, for instance, for 4 elements. And then we say we're going to do a quadrature feeding for all of them. So we bring in a signal, and then we split it 4 ways where we delay the phase shift by exactly a 90-degree from each other. And a 90-degree, as you know, this is exactly the phase shift you would encounter when you go through a quarter wave transmission line. And that's basically what really the sequential rotation based signal splitter is. So you could do that at one level where you can do that to 4 elements, and you could do it at the 2-level sequential rotation, where you actually, in addition to rotating between the subarray of 4, if you go, for instance, for 4 by 4 elements, 16 elements in here, you do the same thing. So basically this quadrant is 0. All of them are 0 degree from these elements in here. And these elements in here are 90-degree difference from these, and these ones, so forth. So sequential rotation is a common way really to generate circular polarization signals from linear polarized batches. That's one, but in most cases, it's really used to improve the radiation performance of circular polarized antennas, mainly to try to cancel out the mutual interferences and end up with the better axial ratio of those. Now, how do we split? So here is how the circuit level design for the splitter. Basically, what we do is we have, in this case, for 4 elements, we have the 4 elements. We come and feed the signal, and then we go through crescent suctions of 90-degree transformers that would leak out the signal, feed the signal, split and feed out the signal to each one of the elements. And by doing this, we're really delaying the phase by 90 degrees from each other. So what this is really here is a 3-way, is 1, 2, 3 T-splitters that are circularly placed in a pattern so that the signal is according to this scheme here. So what we do is we feed the signal in here, and then we come in and we put the first antenna here. That's one quadrant. We have a quarter wave transformer, and then feed the other antenna, the next one, second one. And then we have another quarter wave, and we feed the third one, another quarter wave transmission line, microstrip line, and then we feed the last one. Of course, these lines in here are the same length, all of them, in theory, at theory level. But when we design them, we model them, we do parasitics and so forth, we have to really tune the lengths a little bit from each other. So, and that's what you see in here. And of course, they have the theoretically same length, but the impedances are different because, as you know, when the signal comes in here, we split, first of all, 2 ways. We want each one of these elements gets 1/4 of the power. So meaning that first T-junction in here, we leak 1/4 of the power to this element in here, and then the 3/4 of the signal goes out next in this path of the T-junction, and then again we split 1/4 of that to antenna 2, and then again we split 2/4 of that to the other 2, and then we again split 1/4 here and 1/4 in here. So you can see that the splitters in here is really what determines the impedances. The power split ratios is what determines the impedance of these lines in here, or the quarter wave lines. Now, schematically, and that's what we covered last session, one of the last 3 sessions, one of them was completely for T-junction designs, and we will elaborate more right now. So the equivalent of this, schematic-wise, is really this. So we come in and we have a parallel load in here, this one here, that's the load of the first element. Of course, the elements, they all have the same impedances, okay? So remember this, recognize this. We have, all of the elements are designed so that we have the same impedances on all these lines. So these lines in here all have the same length and the same width, okay? Because they're same impedances. And of course, now it's up to you whether this line here is really the impedance of the antenna, or you can use it as a quarter wave, extend it as a quarter wave transformer to do matching for the antenna batch. Okay, so we have the first element in here, which is this one here. And then we go 90 degrees, and that's this line in here, 90 degrees. And we encounter another load, which is here, this load. This is second element. And then we go another quarter wave, and we face another antenna in here. And then we go another quarter wave, and then we face that last one. So we've got 1, 2, 3. Those are 3 quarter wave transformers that separate the 4 elements. In a lot of cases, we have another quarter wave in here, and I will show you that in a minute. And the purpose of that is to transform the impedance looking into this whole network to the system impedance, which is in this case 50 ohm. And that's basically what you see here. You see this wide line in here? That's a transformer that transforms the impedance between this and the other equivalent network. So again, now we go from, you can see the diagram in here. We have a network that has basically 4 discrete phase shift levels, and at those points we diverge into an element, antenna element, and therefore what we do is we have, in this case, we are feeding here and we're going this way clockwise, and that's called the designation that is because you're doing the right hand, so you're going this way, so you do, it's the right hand side circular polarization. And that's the microstrip. Of course, the impedances vary, and you can see that in here. And we'll show you how we come up with these dimensions right now in a minute. So geometrically, we have 4 elements that are fed in a quadrature, basically. And that's what you see in here. So this is concept, this is the layout, and this is the actual thing. Now, of course, we do that for 4 element or 2 by 2 array, but then we can do 2-level sequential rotation, and that's basically we can have replicate 4 of this network in here, and then have another sequential rotator in here. So we feed right this point here, and we go into this subarray here, and then next this subarray in here, which has a separation of quarter wavelength. So this one is 0, this is 90 degrees, and we're going clockwise again. And the rotation in here has to be exactly the same rotation that is in the subarray, okay? And you can start repeating this on and on for, larger arrays. Like in this case, this is 2, 4, 6, 8. So this is 64 element array. And that's basically, we can go from this basic structure that is where we rotate clockwise in here, and likewise we can do this whole network is fed at the middle in here and rotated in the same direction, okay? Now we can go ahead and do that also for larger ones too. Just to show you here is that the difference between a single rotation and double rotation. So what we have here is, this is for an 8 by 8 array. So we have the sequential rotator in here and a sequential rotator in here at the sub-array level. Where in the other format, we may have only a single sequential rotator at the sub-array level. And in here, we only have a T-splitter. So it's in phase. The signals at all of the sub-arrays are exactly the phase shift, where we have in here, they're different according to this rotation sequence. We do the same thing for larger 16 by 16 arrays as well. This is 256 elements. And you can see here that we come into the middle and we feed, here's a sequencer. We go out and split 4 ways in here, and then we have another sequencer at this level, and then another sequencer in here. Well, this one is, we're using T-junctions basically. So fabrication-wise, this is really what, this is an example from the open literature. So basically the feed point is here. That's the feed, it is in the bottom through a coaxial line or some kind of connection to here. And then this way we feed first to this subarray here, which is 4 by 4. And then we have a quarter wave transformer in here up to this point, and then we feed another subarray and so forth and so forth. So this is, again, right-hand side. There's another example in here that shows, here's the array, the elements, and these are just the parasitics on top, loading these ones. And you can see here, again, we're feeding exactly the same thing we're doing. So we're really coming in here, in this coaxial connector in here, and we're feeding this one first, and then this one, and this one, and this one. So this one is going this way. So this is counterclockwise. So this is left-hand sided, right-hand circular, left-hand side circular polarized. Okay, the same thing is done at the 4 elements. And these, of course, look funny, but these are corner wrap, cornered square batch, which is for circular polarization. Another example in here that I saw in the literature, and of course we come in here, we rotate, and then we do that again. Although this one here, I see there's an issue in here. This is shorted to this. I don't know whether these people realize. I hope they didn't fab this, but this is just It's just an example from the literature. So how do we design this sequential rotator network? It's pretty simple. So the first thing we have to do is we have this network in here. The feed point is here. We know that this is 0 or 50 ohm in here. And what we need to do, we have a T-junction here that splits the power, 1/4 of the power here, 3/4 is here. So that's a first split. So the first split is diverse the signal so that it's 1/4 versus 3/4. That's a two-way splitter, asymmetrical, an unequal power divider that splits the power 1/4 and 3/4, like you see here. And then we have a quarter wave line, and then we get to the next split. And the next split, of course, is 1/4 and 2/4, or 1/2. Okay. And the second one, again, the last one is always equal power splitter, because the last two elements, we get 2/4 of the signal here, 1/4 of it goes here, 1/4 goes here. So we come in here, 1/4 here, 1/4 in here, 1/4 in here, 1/4 in here. All of these lines, even though in this, I captured this from a publication that has different width lines for the antennas, but really in 99% of the cases, the batches are exactly the same impedances. So these lines all have the same impedances, and that's what I'm going to show you in a minute in the design example that I have. And that's basically in here. If you look at the layout of this, okay, so the layout of this, as you can see in here, these lines that feed the antenna elements are all the same, okay? So, but let's go ahead. So how we design this? We design this, we know the impedance at all of these ports, and we know the power levels split between these two ports. At every port, we know the power at every junction. So what's left is to find the impedance of this line, and this line. These are three quarter wave transformers, and then there's a fourth one in here, even though this one doesn't show it. But at this point in here, we're not literally 50 ohm looking in, because we have this here, this element, input impedance in parallel to this one here. And that, we have to figure out what that is and use a quarter wave between this point and the feed line point. Now, how do you figure out the line of these ones? These ones in here, of course, they're circular arcs. They're pieces from a circle. And the way we define these is by using a radius with an angle to determine the arc length. And the arc length in here has to be a quarter wavelength. And as you can see in here, I showed it. This is from high school level geometry. The arc length from 2 points on a circle of 2 pi r circumference is basically really the angle times the radius. So you take the radius and then the angle in here, and you multiply them, you get the length of this here, and that's exactly what we follow in here. So we know how long it is because we know the frequency we're operating at, so we can figure out what wavelength dimensions are, okay, either in degrees or in millimeters, mils, and then come in here and say what is the radius and the angle to correspond to that, okay? And that's basically the formula in here. So this arc in here, or the arc in here, is really phi over 360 degrees all around of 2 pi r, okay? And that leaves you with an angle that the L length is equal to the angle times the r, okay? And that's basically leaves you out with full design equations. So you can figure out how you determine the angle and the radius. You can figure that out after you have calculated the quarter wave length of this. And once you find the impedances of all these lines, okay, then you just go to a microstrip calculator or the line link in link line in ADS or any other tool to find out, using this whatever substrate you're using, to find out what the width corresponding to that impedance. So just as a refreshment, these are, I believe this is from Posar book, I'm not sure, but last time we showed, because all of these are T-junctions, okay, and the equations to determine the impedances of these quarter wave lines okay, is based on a T-junction formula. And the T-junction formula, you can please watch my back videos. So basically, the impedance was calculated, which is Z1 and Z2, that would split the power unequally based on some kind of power ratio, which is the ratio of the power on port 1 versus port 2, port 2 versus port 1. And that's basically these equations in here. So we've got a K, which is basically the ratio of the power. So the P out is P1 plus P2, which is exactly equal to Pn. Also, we're assuming it's lossless right now, okay? In actuality, it is not, but the loss is common to both sides, so it doesn't matter. And then P1 is KPN, so the K here is the ratio between the output power in here versus the input power, and the output power in here versus this one. Or if you define it from here to here, then one minus that is basically the other leg, because we're assuming it's normalized to 1, the input power level. And then from last time, we said that we can, right away, we can see what the the quarter wave transformer that transfers from the output impedance to the T-junction equivalent virtual impedance by these two equations in here. Please refer back to that video. So how we do that for this here. So what we have this network, we're feeding at this point, and let's take one junction. So this junction, this junction, or this junction in here. So basically we split, and this is a splitting. And we know the power on port 1 and port 2, and it's equal to this, which is basically the square RMS voltage divided by that impedance. And the same thing in here. So if we take the ratio of these two powers at this port and this port, which is here, we divide these, the 2V0 square is gone in here. We cancel those because they're common to numerator and denominator. And we end up with this equation in here, which says that the ratio of power to port 1 to port 2 is equal to the impedance on Z2 to Z1. Sorry, there's a sign in here, a straight sign. So this is Z2 over divided by Z1. So this is all you need to define the impedance for these lines, because you know what port 1 and port 2 are, the power levels according to this. So you know that this is 1/4 of the power here and 3/4. So 1/4 to 3/4 is equal this impedance over that impedance, okay? This impedance over this impedance. Well, this impedance here is known. We know that because that's the antenna element impedance. So therefore, it falls out. You can calculate what this impedance has to be so that the unequal power splitting is according to this relationship. And that's basically what we did. So let's take an example in here. This is a network, okay, that I have 4 elements schematically representing this. This here is a representation of this in here. So we feed in here, and then we go around 4 ways connecting these. And so we've got 4 antenna elements. Each one of them is getting 1/4 of the power, equally dividing the signal to them, okay? And then, so we know the input impedance to this, which is 120 ohm in this case. Every one of them is fed by that. And we know the phase shift in there, even though it's irrelevant at this point, but all of these are fed. The first one is 90-degree shift from the source. The second one is 180. The third one is 270, and the last one is 360 degrees, okay? But if you look at these, between this point and this point is 90 degree, between this point and this point is another 90, and between this point and this point is 90. So therefore, these are covering the full quadrature, 4 quadrants of the 360 degrees. So we come in here, we have 50 ohm known in here. We have let's look at the first junction. We're splitting so that 1/4 of the power go in here, but 3/4 goes here. Why 3/4? Because we have 3 elements to deliver power to. So 3/4 of the power has to go this way. So we know that this T-junction splitter in here splits the power 1/4 to 3/4. So we know this ratio, we know this impedance, and therefore we can find out what Z2 is. Leave out Z1 for right now. Z1 is a transformer that will transform the equivalent impedance at this junction to 50 ohm using quarter wave length. So we can see now then 3,4 divided by 1,4 is equal 120 divided by Z2. And then we can solve for Z2. And you can do the same thing for all of these, okay? So that's basically how we go from here to here conceptually and then on. And I did this with hand calculations right now. So just was lazy to type this using a math editor. So basically, here's the network again. I drew it. We have 120 ohm on each leg. We have 1/4 of the power here, 3/4 of the power here, another 1/4 here, another 2/4 in here. The 2/4 in here divides between the two last antennas, 1/4 of the power and 1/4 of the power. And let's start junction 1, junction 2, and junction 3. At junction 1, the ratio of the powers between the two this element and the power delivered to the three other elements is 3/4 divided by 1/4 of the power. So cancel out these. That should equal 120, which is this impedance, divided by this impedance. And that's what we defined basically in here, based on this equation here, okay, which is for the T-junction. And you can refer back to my other videos to see this. So we simplify this, so that's 3, and that's 120 over Z2, so therefore 3 Z2s equal 120, that Z2 in here would have to be 40 ohms, okay? Let's do this to the second one. The second one, we have half of the power in here, which is 2/4 of the power in here, and another 1/4 is here, so we got 1/2 divided by 1/4 is equal 120 here divided by Z3 here. And that leaves you with the equation here, 2Z3 equal 120 degrees, and that's basically 60 ohm. We do the same thing at this junction. This junction here, of course, is different because the power is equal. This is here always going to be 1, which means that always the impedance, this impedance always is going to equal the impedance of the antenna, the last element feed. And that's obvious. We can see here is because we have, this is a T-junction splitter with that is equal powers. So meaning, and so that therefore the two impedances has to be equal the same. Okay, and in this case, the impedances that feed the elements are other. So we solve for this. So that means that's really this impedance in here, this impedance, and this impedance. So we still have one more line, which is this line in here, and that's what's going to match the entire input impedance to this network with the input impedance of 50 ohm. So, and that schematically, you can draw this in here. So this is Z1 in here. It's a quarter wave, which transforms 50 ohm to whatever the impedance looking at junction 1. And if you look at this, that's basically, we've got 40 ohm in here, and we've got 120, and that leaves you with, these are in parallel, so that's a 30 ohm. And therefore, this transformer in here is really the square root of 50 times 30, which is 38.7 ohm. So since this is 40, that's 38.7, I went ahead and said, well, make this 40. So I made this 40 and this 40, so therefore, these lines are, okay. So let's go ahead and look at how you model this network after you figure it out. Of course, we have all these impedances, so, and then we did a hand calculation. I did a hand calculation to do the length of this, because I know the length of this, and I know it's an arc on a circle, so I can figure out what the angle is that extends out of 360 degrees that corresponds to that arc length, or the length of this line, which is 90 degree or quarter wavelength. And of course, the radius is equal on all of them. So that's what you get in here. So I got in here, this is my input, which is 50 ohm, and the other 4 outputs are all 120 degrees. So that's 120, 120, 120, all these loads are. And then I come in here, and there's a line which is 50 ohm. That's arbitrarily chosen. I could choose any length. That's what comes from, if you look at the examples in here, that's basically what comes, in this case, the feed line, okay, which is, let's see, where are we feeding in here? Where is the feed? The feed is here. So that's this line in here, Okay, this line in here. So that one is arbitrarily designed. The length of that is arbitrary. You can choose any length, it doesn't matter. The first 90 degree, that's L19 here, where I define the variables in here. These variables are defining L90 is equal in here. So we defined that, and that's basically 50 ohm. And then this one is the 39, the line that corresponds to whatever this 39 ohm in here. Okay, I have a T-junction, and then I have the first arc that loads the first antenna. Okay, and that's basically this guy here. Okay, so this is the line that transformed this 50 ohm in here to the impedance looking into the whole network. Okay, or here I did the drawing in here again. So basically that's this arc in here. The next arc is basically this, and again you have another T-junction here. It splits to this element, and then another arc, and then you split to the third element, and a fourth arc that is basically under. So you can see the impedance in here and in here and in here are very close. Okay, and of course if you look at the S12 1N parameters, they're all 6 dB, of course, in this case close to 6 dB, and that's basically what you get because it's a four-way splitter. Now the phase shifts on all of them, you can see them here. Basically we got 0 degree, 90 degree. Actually this is normalized. You subtract the, so if you take what I do is I find the phase shift on this element in here at a particular frequency, and then the other ones I plot the subtraction of the actual phase shift on that line. That's what you see in this equation here. You take this particular port phase and you subtract S21 phase shift from it, and that's what you end up with is the degrees. You can see they're very close, 90 degree between the first and the second, 180, which is 3 degrees difference, and then 280, 270. So you can see that the last one has got a little bit, you have to tune it, okay? So basically when you end up with this, this one, you put it on the optimizer. So the optimizer, what you do is you say, I want the power level on all these four to be equal, okay, which is 4 dB below, 6 dB below the input power level. But then I need the phase shift difference from this point, the first feed, element feed, to be exactly 90 degree here, in here 180, and in here 270, okay? The return loss is good. I did this for 25 gigahertz, okay? And so let's go ahead and look at the network in here. So let me close this. So this is what I did here. So the substrate I used, by the way, just so if you're interested, is Duroy 2.2 Rogers material. That's 0.2 for a quarter millimeter height. Okay, and this is what you see in here. So all of these are right now loaded with 120 degrees. Okay. So let's go to this guy here, since we have figured that this guy is really the phase shift. Let's simulate it first. So what we have right now, this guy here is this is the absolute angles where I subtract the first angle. So the angle of the first element, I subtract from it the other ones, and you end up with these degrees in here. So the first one is 0, I subtract from itself, and then the second element is 90 degrees, and then 180 to 180, that's fine. We can still come back in, but this one here is 287. It's got about 7 degrees of difference. So what we're going to do, and of course the layout for this, let me just show you the layout. We can produce the layout for this, and that's what you end up with. Okay, so you got these are the arcs and these are the lines that comes in between them. That's the feed line in here. And this is the last one. Of course, realize this, I did not mention it. This last thing in here is really a corner, okay? A microstrip corner, where the other ones, of course, is basically a T-junction. And that's what you see in here. This is a T here. See this T here? The width of this is this width, and that width, which corresponds to the three-way width. Okay, so let's go ahead and come back Don't save this. So what we're going to do is we know that this one is giving an additional phase shift, more phase shift than we have. So 287, and what we want is 270. Okay, so we've got about 17 degree that we need to do. So we're gonna reduce this basically. Let's reduce it to 80 first and run it. And this is a poor man's optimizer, just tweaking by hand. In actuality, you really want to run this using optimizer. So let's see what happens. So the phase shift in here is 281 degrees. Okay. So it did go a little bit, but it didn't go fully. So let's go back and undo this and run it back again because I forgot what the number was. So 287, and if we put it back on 80 degrees, we reduce by 5 degrees, 5, and that's 281. So okay, so we didn't get back there. So we still have 10 degrees. So we can go, let's say 75 degrees on this. And let's simulate it. And hopefully this time we're closer. And that's basically what we see here, 275. Okay, so we still got 5 degrees. So let's go back and reduce it to 70 degrees. And we'll keep the radius the same. So we're just basically reducing, okay, 269. So we're done, okay? And we still have the return loss, same way. We still have the insertion loss is basically 6 dB and so forth. So this works, and that's basically, so this is how you design this, okay? And so again, this is really how we started out. What we covered today is basically the sequential rotation-based network, feed network, and which is this topology in here. This is a system diagram that shows all it is just a circular network of four-way splitting with quadrature phase shifts between all the elements. And that's what we see here. And we showed the equations on how you would design that, which is based on this principle in here. And then you can get exactly what these lines should have impedances. And according to this, of course, this is, I didn't read this when we covered this. So basically this network in here, the power ratio is always known because we know what it is. We know we need 1/4 of the power on each element, okay? And therefore, when at the first feed, we know that it's a T-junction of 1/4 to 3/4 splitting, okay? 1/4 of the power to 3/4 of the power, or 25% of the power to 75% of the power. And the second one is 1/4 to 2/4. That's this junction here. And then the third one is an equal impedance junction, okay? Because the power we got at this point, it has to go halfway between this port and this port, okay? So the other port is what needs to be calculated, meaning we know this port here loaded with the element impedance, which is known. The antenna array designer gave you that value. So the feed network designer comes in here and he has to be giving all these impedances. And if you want to be really accurate, he would give you the exact impedance looking into every one of these antennas, okay? Every one of these elements at this point here, of course. But in theory, they have to be all equal, okay? All right, so that's it, ladies and gentlemen. This is Mohamed Nezami, Dr. Mohamed Nezami. Again, I'm an RF microwave independent freelance design consultant. If you have any contract work that you need to offload your home RF designers, RF microwave designers, or if you don't have one, from a cost point of view, you could come to a guy like me, and I will work with you from concept to fab files, anywhere from DC to 35 gigahertz. So this is it, ladies and gentlemen. Please, I would really urge you to go back to my channel in here, and please go ahead and subscribe to the channel and share these videos if you don't mind on between your associates, and also watch the other parts of this to get the full benefit of this. I also have other videos on various network systems that are known here. Okay, again, I would like to thank you all for having put up with me on this series of flat or planar antenna feed networks. We've covered networks that were based on the T-junctions, and then other networks that were based on the Wilkinson dividers. These are the most common two, and some even, I showed some examples of how you would do this to some mix network feed lines. So we'd appreciate that, and thank you very much, and we'll see you on the next video. Thank you again.